Hello everybody, getting ready to do lesson 8.6 part 1, pre-calculus math today. And for today's lesson in our notebook sheet, you have 8 points on your notebook guide and then 52 points on your classwork sheet. Have those out in front of you. Name, date, period if you're online or you're a homeschooler, put your due date here. Part 1, 8.6, probability. And today's bell work, students, teachers, here's your bell work for today. Evaluate NCR, verify your result using a graphing calculator, okay? So here you have 73, 74. This is from your previous lesson, students. Teachers, give your students about 5 minutes. Welcome back for your solutions for today's bell work. 6 choose 2. Here is your formula for that. Remember, students? And that comes out to 15 for number 73. And then for 74 here, and choose 5. When you crank this out here, these will cancel. And you come out with 126 for 74. To today's lesson, we'll go right into a notebook here. The probability of an event. Any happening whose result is uncertain is called an experiment. The possible results of an experiment are outcomes. The set of all possible outcomes of the experiment is a sample space of the experiment, and any subcollection of a sample space is an event. For instance, when a 6-sided die is tossed, the sample space can be represented by the numbers 1 through 6. So with a 6-sided die, 1 through 6, for the experiment to be fair, each of the outcomes is equally likely, right? So to describe a sample space in such a way that each outcome is equally likely, you must sometimes distinguish between or among various outcomes in ways that appear artificial. What does that mean? Well, finding the sample space. So we have a sample space here. Let's find a sample space for one coin is tossed. So because the coin will land either heads up, denoted by H, or tails denoted by T, the sample space for a coin toss would be HT right here. So your sample space would be HT. And then for 2 coins are tossed, because either coin can land heads up or tails up, the possible outcomes are HH, which equals heads up on both coins, and HT, heads up on first coin, tails up on second coin. 2 coins are tossed. So begin continuing with that. TH would be tails up first coin, heads up on second coin, and then TT will be tails up on both coins. So the sample space is this for 2 coins being tossed, HH, HT, TH, and TT. That would be the way that you would designate that, write that sample space out. Note that this list distinguishes between the 2 cases, HT and TH. Even though these 2 outcomes appear to be similar. Okay, 3 coins are tossed. So following the notation in part B, the sample space is, here we go. Now we got 3 coins here, so we have 3 different possibilities here. We'll designate a specific occurrence of 3 coins being tossed. Note that this list distinguishes among the cases. So the key word here is distinguish. HHT, HTH, and THH. And among the cases, HT and T, THT and TTH, let's see what we got here. Determine the sample space for the experiment. A coin and a 6-sided die are cast. So we have a coin and a 6-sided die. So determine the sample space for this experiment here. Students, this is yours down here. We're going to do this one now, our guided practice. So for a coin, we have H1, H2, H3, H4, H5, H6, And then for a tail situation, T1, T2, T3, T4, T5, T6. So that would be your sample space here for a coin and a 6-sided die. To calculate the probability of an event, count the number of outcomes in the event and in the sample space. The number of equally likely outcomes in event E is denoted by NE, and the number of equally likely outcomes in the sample space S is denoted by NS. The probability that event E will occur is given by NE divided by NS. The probability of an event. If an event E has NE equally likely outcomes and its sample space S has an NS equally likely outcomes, then the probability of an event E is given by probability of E would equal NE over NS. Okay, so because the number of outcomes in an event must be less than or equal to the number of outcomes in the sample space, the probability of an event must be a number from 0 to 1 inclusive. That is, 0 is less than or equal to probability of E less than or equal to 1. As indicated, so here is an example. Here's a way to visualize this. Impossible event would be 0.0 chance, and then the occurrence of the event just as likely as unlikely, a 50-50 would be 0.5, and then a certain event must occur, be a 100% chance that it will occur. So again, here's our scale. If probability of E would equal 0, that would be your mark there on that scale. Then if probability E equals 0, then event E cannot occur, and E is called an impossible event. If probability of E equals 1, like here, way up there, then event E must occur, and E is called a certain event. So if it's 1.0, it would be a certain event. Finding the probability of an event. 2 coins are tossed. What is the probability that both land heads up? So, following the procedure in example 1b, let E here be HH. That would be our situation. In our sample spaces here, we got 4 different possibilities here for this one to occur. So the probability of getting 2 heads would be probability of E be NE over NS would be 1 out of 4. So it'll be 1 out of 4 here. Which is the same thing as what, class? 25%. A card is drawn at random from a standard deck of playing cards. What is the probability that it is an ace? Because there are 52 cards in the standard deck of playing cards and there are 4 aces, the probability of drawing an ace is probability of E be NE over NS, be 4 out of 52, be 1 out of 13. So to find the probability for the experiment of tossing a coin 3 times, then here's our sample space. The probability of getting exactly 2 tails. So the probability of getting exactly 2 tails. So in this situation here, tossing a coin 3 times. So for that one, so we have heads, tails, H tails would be tail, heads, tails, or tails, heads. So our possibility here out of these 8 possibilities for getting exactly 2 tails will be, we have 3 opportunities out of 8 would be our chances experimentally of getting exactly 2 tails from that. The probability of getting a head on the first toss, that's yours, students, so go for that. Note that a probability can be written as a fraction, decimal, or a percent. For instance, in the example 2a, the probability of getting 2 heads can be written as this way: 1 over 4, 0.25, 25%. You could have written out sample space in example 2b and simply counted the outcomes in the desired event. For larger sample spaces, however, using the counting principles described in section 8. You could save time by just writing it in a percentage. So finding the probability of an event, 12-sided dice can be constructed in the shape of a regular dodecahedron, such that each of the numbers from 1 to 6 appears twice on each die. Show that these dice can be used in any game requiring ordinary 6-sided dice without changing the probabilities of the various outcomes. Okay, well, for an ordinary 6-sided die, each of the numbers 1, 2, 3, 4, 5, and 6 occurs only once. So the probability of any particular number coming up is 1 out of 6. So for 1 to turn up, it'd be 1 out of 6. So in this one here, 23, the sum is less than 11. So again, we have to use sample space from exercise 10, which we just did, to find the probability for the experiment of tossing a 6-sided die twice. So when we throw a 6-sided die twice, the sum is less than 11. So what would be the probability of that happening? Less than 11. So not E would be 5, 6, 6, 5, and 6, 6. That would be not E. But E would be n of S minus n of not E. So it'll be 36. We have 36 shots here. And we subtract 3 from that. And we get 33 now. So probability of E would be 33 over 36. Or simplified 11 over 12. That would be our probability of getting a sum less than 11. And then down here, your sum is odd or prime. Try that one, students. Okay, so moving right along here. Example 4, random selection. The number of colleges and universities in various regions of the United States in 2008 are shown. So here's our map of that. One institution is selected at random. What is the probability that the institution is one of the 3 southern regions? So, okay, our southern regions, here's one, south, south, and south. Okay, so we got 3 different southern regions. So the total number of colleges and universities is 4347. Because there are 1,446 colleges and universities in the 3 southern regions, the probability that the institution is in one of these regions is 1446 over 4347 would be 0.333. Okay, let's try one now from that. The winner is 19 to 39 years old, and we're going to use this, our pie chart here, as our amounts of facts of certain ages and certain categories. Ages of season ticket holders. So the winner is 19 to 39 years old. One of a team's 2,200 season ticket holders is selected at random to win a prize. The circle graph shows the ages of the season ticket holders. Find the probability of the event. So what is the probability that the winner is 19 to 39 years old using this pie chart here? So we got 792 ticket holders, 19 to 39. Where are we at? 19 to 39, 19 to 29. Oh, so we add these two together. So when we add those together, we have 792. See, 792 ticket holders, 19 to 39. 18 or younger, 66, 19, so 264 here. This is for 18, okay? So add these two numbers here, and you get 792. That comes out to 9 over 25 for the probability of this happening. And that's 8.6 part 1, pre-calculus math. Here is my email if you need course materials or information. Animated PowerPoint math video at AOL.com. Thank you very much.